Я сейчас уберу, я скопирую и буду. Блять, я забыл, как это. Regionale, la spesa, prima quando c'è in a train for 2 hours. It was hot stuff. Yes. We also have southern.
You're an engineer, you have to know how to get
Vediamo. Grazie. So it seems that you are very interested in the mid-term test, and 3rd of May, there is an interruption of lesson. This last week of April and first week of May. 1st of May is Monday. Good. 3rd of May, Wednesday, is the good. For those that are interested. It is on the first part of the course. It is what we do until Wednesday, 12 April. And mainly exercise. You're engineer. I'm sorry, but I cannot. You choose, not me. Huh? Midterm
Will be based on exercise.
exercise, numerical exercise. Yes.
You will do any kind of exercise session?
Before. No.
Thanks God.
So have some
You have
sort of,
18 years of school behind you, so you know.
We hope so.
so can you have some sort of previous example?
Just put the number in the footnote, it's not a big deal.
It's the possibility of making it on the if we do the midterm and we are not satisfied with the grade, is it possibility to have the whole oral?
If you're not satisfied or you fail, there is the entire exam in July, end of the year. Okay? You can bring notes, but clearly the level will be a little bit higher. So, well, for me it's fine. Up to you to decide.
How many exercises?
Probably, I don't know, 3 or 4. 4 simple, 3 a little bit more complex.
Can they do the coupling?
About everything till Easter. So, probably the Maxender, the AWG, ring sonator.
And the whole like what is made by
Probably. No. Allora, there is um, 12th of April is the last lesson. Then there is the Easter vacation. The Easter vacation. Then there is Wednesday 19 alone, and then 2 weeks of stop. So we do not have a lesson, just April 19, but one lesson in the middle of 1 week before and 2 weeks after does not make any sense.
April 19 have this or don't have this? This is
No. Possibly we can do some exercise.
yeah.
Okay. Can I continue? Any questions? Now? So I summarize once again very quickly. Huh?
Just one quick question. Just to know what to do with numerical exercise. Delta N1, delta N2, in our case are the NW of the slab, because in that part of the NW, because
is the refractive index of the directional coupler minus the refractive index of the other waveguide. So this is NW minus NS for NCM.
Also for the name that, for example, we said delta N1, then we do NW minus N1, right?
Yes, sure.
Because there is only N2 in that time. That's why we, give a name like delta N1. That's why I asked.
1 and 2 is the name of the two waveguide.
Yeah.
Then I assume the two waveguide identical. Because it's easier, no? And W and S. Then you can think the two waveguide are different. We will do it when I give you the final solution. But in this moment, I'm more interested in wave equation. Put in the wave equation the approximate solution, so the combination of the two modes of the waveguide itself. You get an equation that separates in two simpler equations in the system. When you do this, some coefficient appear. So the physical meaning of the coefficient, and then the solution that we do now. So think always the directional coupler as a structure with its proper mode that propagate independently one to each other, or these two proper modes described as a linear combination of the modes of the two waveguides taken separately. I'm boring, I know. Continue to say the same thing. So now we have to solve this. I think that I can cancel. Okay. To solve this system, it's convenient to think to the solution as really a mode that propagates. So an amplitude A equal to the decay. I just change the variable. And we consider a variable like this one, and small b equal to b. Okay, we think to this change of variable. So we now substitute a big A, a big B with that one. It's not a big effort. You just have to do a derivative here. and we get this system. I neglect K11 and K22 because they are small. So this is the new system, and here you can really see very well that the amplitude of A depends on A and is perturbed by the amplitude of the other mode, by this coefficient that is small because it's just the tail of one mode, and the same for the other one. If the waveguide goes very far away, this one vanishes, becomes 0, and so A is just, you see, this one. The solution of this differential equation is an exponential, is exactly this exponential. Because the derivative of A, if A has this form, is A multiplied by the exponent, J beta. So, now continue the solution. So we know that we solve this. So now we solve this system. So to solve the system, I assume that we start with an amplitude A0 multiply A minus J beta zeta B zeta B0 minus J beta zeta. So I put these two inside this system, and I get, if you substitute, you have to do the derivative, and what you get is this. This part is not more useful. So this system, they are known the two amplitude and beta. So this can be written in a very familiar, I guess, way. This way. Okay, I'm doing all the
Mathematical detail, passaggi.
You are happy. And you, what is this? How do you call it?
Matrix. Yes, sure.
and vectors. This is an eigenvalue problem. You recognize? This is an eigenvalue problem. So the solution, the eigenvalue and the eigenvector are the solution of the problem. Eigenvalue means the determinant of this matrix equal to 0, and you calculate beta. And what you get is beta, I use some space, equal to beta 1 plus beta 2. I assuming now the two waveguide different. So the most general case. Divide by 2 plus minus beta 1 minus beta 2 divide by 4 to the square plus k1 to k2 1. So these are the eigenvalue. This is an eigenvalue problem, so you have eigenvalue and eigenvector. The eigenvector are the field, no? The meaning of this A and B are field, so the eigenvectors are the solution, and the physical meaning is the field of the solution. That is the two modes of the structure. So the symmetric mode and the antisymmetric mode, or even mode. So I can write here S or A, symmetric, antisymmetric, or if you prefer, even and odd. Sometimes I use even odd, sometimes symmetrical and antisymmetric. Let's try to stay on symmetric and antisymmetric. So these are the eigenvalue. So the phase constant of the two modes of the structure, symmetric and antisymmetric, expressed as function of the phase constant of the mode of the two waveguides separately, perturbed by the coupling coefficient. So maybe a little bit heavy today, a little bit complex, but you can see immediately how powerful is the coupled mode theory. We have not to solve the wave equation for the directional coupling. We just take the characteristic of the waveguide alone, and if we are able to calculate the perturbation, and we are able, we get immediately the phase constant of the mode, the real mode of the structure, without solving the wave equation. That is a good advantage, no? The eigenvector is, I write the first one, then
refractive index is now squared.
because before I forget to put the square, because and now I correct. But on the note is correct. In the wave equation, what enter is the dielectric constant. So n to the square. So that's not really important. The physical meaning behind is more important.
How we define A0 and B0? How do we the amplitude of the how do we define A0 and B0?
A0 and B0 are just the amplitude of the solution, so are totally arbitrary.
So if for an arbitrary A0 and B0, we can find the solution. For an arbitrary A0 and B0, we can find the solution of 4. So if we put A0 and B0 equal to 1 for example,
what is important is the relative amplitude of the two. The absolute is related to the power, the absolute power, but we are not interested in the absolute intensity or absolute power. No? So this tells you only the absolute power or absolute intensity. These are the eigenvalues. The eigenvector depends on A0 and B0, but clearly you can normalize to on something, no? So I was writing here the this, for example, can be written this way: J beta S delta Q A J delta A. So these are the two eigenvalue. It's important to know which is the physical meaning of the eigenvalue. And then the eigenvector. I wrote just the first eigenvector. I don't write the second one. You can find on the notes. It's not very important. What is important is to notice that the amplitude in the waveguide A, in one of the waveguides, depends on zeta, on the position along the structure, the directional coupler, and depends on the amplitude of the symmetric and antisymmetric mode, even and odd. So once again, we found the solution, the approximate solution, and the rigorous solution related by a simple combination, a simple linear combination of the solution. So the amplitude in one of the waveguide, the first one is A. It depends on the position because it's not a mode. This one, right? So you should not be surprised to see this dependence, and is a combination of the mode of the structure, symmetric and antisymmetric. Each mode propagates with its own phase constant. They are different, and these two modes are real mode of the structure, so these two are just coefficient. Does not depend on the position because are the modes. So I need now another step and we basically arrive to the final solution. It is probably the last complex expression, complicated expression. So now we are able to calculate the amplitude of the field in every point of the structure once you know the amplitude of the two modes and their phase term, the phase propagation, So if you have a directional coupler, you know the amplitude of the mode, so symmetric and asymmetric, and their phase constant. You are able to calculate the amplitude everywhere in the structure. And this one that I have not tried because it's a little bit more complex, and I don't want that to get lost in the formula. Or vice versa. You can calculate the amplitude AS and AA, the symmetric and anti-symmetric mode, as a function of the amplitude in the waveguide, in the upper waveguide and in the upper waveguide, in the lower waveguide. So you can write this one as you like. One as a function of the other one, or vice versa.
So the amplitude of symmetric and anti-symmetric is constant.
Because of the mode.
Yeah, will the A's be constant? Only the phase will change? The amplitude is very wide, yeah.
This is not constant because it's a combination of two complex numbers that change along the propagation, so that their combination change. Is the movie that I showed you before, no?